Welcome to day 71. Today, we're going to dig into a really fundamental question. Why did we even need transformers in the first place? By the end of this, you'll understand exactly why the old way of reading text, one word at a time, hit a dead end. So let's start with the central puzzle. Think about it. If a machine reads text just one word at a time, how could it possibly understand the full meaning of a long story? I mean, it seems like a logical way to read, right? But it creates this huge problem. How do you keep the whole picture in mind when you're only ever looking at one tiny piece? Well, this problem has a name. It's called the sequential bottleneck. See, the older models, things like recurrent neural networks, or RNNs, and even their smarter cousins, LSTMs, they all worked by reading text pretty much like we do, one word at a time, from left to right. And it sounds intuitive, for sure, but this approach has a massive weakness, and it all comes down to memory. Okay, so imagine a model is reading this text. It reads, "I am from Italy," then a few more sentences. By the time it gets to the very end and has to predict the next word after "I speak," that key piece of information from the start, Italy, has basically faded from its short-term memory. It really struggles to connect the end of the text to the beginning. This is what we call the long-range dependency problem. The important context just gets lost over long distances. So you can see the engineering challenge taking shape, right? The old way was just too slow. It forgot context over long sentences, and it was a real pain to scale up for training on huge amounts of data. What was needed was, well, something totally different. A new architecture that could look at the whole sentence at once, find those long-range connections, and, this is key, do it all in a way that you could run in parallel on modern computers. And the solution was a real aha moment. It was a completely new way of thinking. Instead of forcing the model to remember everything in a single straight line, what if you just let it look at all of the words at the same time? And what if you gave it the problem to decide for itself which words are the most important for understanding any other word in the sentence? This powerful idea is called the self-attention mechanism. And what it does is pretty incredible. It lets the model build direct connections between every single word and every other word in the sequence. Suddenly, a word at the very end of a long paragraph can directly pay attention to a word right at the beginning. Just like that, the long-range dependency problem solved. Here's a great way to think about it. Imagine you're in a crowded, noisy room. You're talking to one person, and your brain just automatically tunes out all the other chatter and focuses on their voice. Self-attention gives a model that same kind of superpower. For any word it's looking at, it can crank up the volume on the most relevant context words and just ignore all the other noise, no matter where those important words are located. So once researchers had this super powerful tool, this attention mechanism, they started to wonder, wait a minute, if this is so good, do we even need the old, slow, sequential part at all? And that question led to a brand new type of architecture, one built entirely around this core idea of attention. This all came to a head in 2017 with a truly game-changing paper from a team at Google. And the title said it all. It was a really bold claim. Attention is all you need. Their big idea was to completely throw out the old recurrent system and just use attention. And honestly, that one move completely changed the future of AI. Okay, so how does this thing actually work at a high level? First, the big one. It processes the entire input all at once, in parallel. This is a perfect job for modern GPUs. Then, the self-attention layers get to work, calculating how relevant each word is to every other word. Now, you might be thinking, if you look at everything at once, don't you lose the order of the words? And you'd be right. That's solved with something called positional encoding. Think of it like adding a little timestamp to each word so the model knows where it came from. Finally, you package all this up into an encoder-decoder structure. The encoder's job is to understand the input, the decoder's job is to create the output, and both of them are just stacked with these powerful attention layers. Now, all this power isn't free. There's a pretty major trade-off. While the old LSTMs scaled linearly, meaning if you double the sentence length, you double the work, transformers scale quadratically. That means doubling the input length doesn't just double the compute, it quadruples it. And why is that? Because every single word has to calculate its relationship with every other single word, which creates this enormous matrix of score. But here's the thing, even with that quadratic cost, the ability to do all that work in parallel was the absolute key. It meant you could finally use massive computer clusters to tackle the problem all at once. This unlocked a scale that was totally unimaginable before, and it kicked off a full-blown revolution. And this wasn't some slow burn academic idea. The impact was immediate. Just a year after the paper, we got BERT from Google. Soon after, GPT-2 from OpenAI. I mean, within just a few years, the transformer went from a concept in a paper to being the literal foundation for pretty much every single large language model out there today. This parallel design was just a perfect fit for hardware like GPUs. For the very first time, it was practical to train a single model across huge numbers of machines at the same time. And that's the reason we could go from models with millions of parameters to the models we have now with hundreds of billions of parameters. That kind of scale it was a complete non-starter with the old sequential methods. So today, if you're using a top-tier AI system, chances are there's a transformer under the hood. And we're not just talking about language stuff like translation or summarizing articles. The same basic idea is now used to generate code, to analyze DNA, and even to create images from text, like in models such as DALL-E. The architecture turned out to be incredibly versatile. So when you boil it all down, the invention of the transformer came from a really simple but profound shift in perspective. It was about this. Stop thinking about language as a straight line and start seeing it as a rich web of relationships. So what's the one thing to remember from all this? It's that the ability to process information in parallel, instead of one piece at a time, was the fundamental unlock. That single change is what made it possible to build the massive AI models we have today.